Well, that was always a thought, always in the design of packet-based networks. Because once you drop the idea that the network is the arbiter, the rationer, the police of using the network, then how do you signal to a sender, whoa, buddy, that's unfair? And so you've got to actually drop further back into going, I have this network full of senders and receivers, and some senders and receivers at the same time, full of a bunch of people producing packets and consuming packets. What am I trying to achieve? Does everyone get 64 kilobits per second of clear channel? Of course not. You get what you need, but there's a couple of overriding tenets. Firstly, everyone should be efficient. What does efficiency mean? Don't leave the network idle if you have things to send.
You're listening to Ping, a podcast by APNIC discussing all things related to measuring the internet. I'm your host, George Michelson. This time, I'm talking to Geoff Huston from APNIC Labs again, in his regular monthly spot on Ping. Geoff and I talked about his recent trip to AusNOG in Melbourne, and a talk he heard there about optimizing throughput and fair shares of a link in the modern fibre optic dominated high-speed network of routers and switches. He's been looking at TCP Flow control models for some time, and recently testing BBR in a variety of ways. And the talk reminded him of an older IP layer model of explicit congestion notification, or ECN. ECN is baked into the IP header and returns signals inside TCP, but it isn't proving viable in the wild. The idea of sending back a signal you're pushing too hard isn't exactly new, but as Geoff has learned, the mechanism isn't working out as well as we might hope. And so protocol tweaks like BBR, which is now in its third iteration, have to try and do a better job of both bandwidth estimation and managing the competition for space in order to be fair. Geoff, welcome back to Ping. What should we talk about this time?
Well, George, I've just come back from the annual Australian Network Operators Group shindig down in Melbourne in September and the start of September. And it was a great couple of days. And, if anyone's cruising around Australia at that sort of time of the year and has nothing better to do for a couple of days, I'd certainly recommend going to drop in on AusNOG. It is great.
Oh, you've got to be quick. Tickets go like that. They're gone in a flash.
They've been sold out for the last 18 years, which is amazing. Just sold out. Very popular. Anyway, yes. And I was talking about the evolution of transport protocols, and I kind of thought, well, unlike other kinds of topics that one could talk about, like V6, why bother? Or RPKI offers about as much protection as an armour-plated suit made of wet lettuce leaves. I thought the transport protocols was a much tamer topic without the controversy that these other ones breed.
Oh, you say that, but I have a feeling it'll turn out not to be the case. But pray continue.
Well, I spoke just after a gentleman from Cisco who was hawking a different kind of transport system based on effectively MPLS, source-based routing, bits of V6, all going by an RSVP, I think, came into it. It's sort of all the bits that are just weird.
Right.
And I'll tell you what, other than the names of the technologies, this was a talk from the 1970s.
This idea, in some air quote sense, better.
Well, it's also an idea that, like speaking into a telephone handset, remember them, the application is inelastic, dumb, and invariant, and will not adapt to any conditions in the network. I've yet to meet those applications. And secondly, then it's left to the network to effectively behave smoothly and consistently and not muck around with the implicit timings coming in from the application traffic.
Well, we've had an idea of smart edge dumb core as a kind of concept in constructing networks for a long time. I wouldn't say it's baked into the IP protocol, but the idea was you wouldn't have massive intelligence in the core of packet forwarding. You'd try to keep that to a minimum.
Well, that was the whole thing. I'm like, if you have computers mediating the application workflow, then you don't need to blindly try and preserve absolute adherence to synchronicity. It's not just a telephone. It's a telephone going through a computer. You quantize the voice signal, you chuck it up into packets, you send it out as packets, but the receiver, also a computer, is not just a speaker.
Yeah.
It firstly goes into an input queue and reassembles, if you will, the analog signal as it assembles out of the local buffer, the incoming packets, and then reproduces a constant voice signal. You and I are having a fine conversation, and dear listeners, you're listening to this in real time, but there's no real-time circuitry. We've carved out a channel. It's got absolutely zero jitter and high fidelity. It's exactly the same as telephony. Not at all.
No.
You're just running packets.
No, this is really quite different to the longer held view from old times about the nature of communication, with the right kind of error correcting and the right amount of buffering, which of course implies delay, but nonetheless the right amount. It's possible to use packets that have no deterministic behaviour to get remarkably fine outcomes. It can be done.
Well, not only can be done, it's the default of what the entire world does today.
So presumably you were talking in a sense saying, well, all this complexity of MPLS and SRv6 and RSVP, there are other approaches. So you have an idea of a simpler approach to signalling behaviour?
Well, I'm reproducing an IP advocacy sort of line from the early 1980s.
Ah, you've come from the 70s to the 80s.
I come from the 70s, yeah. No, I mean, the issue was that you didn't need to put all the investment into the network to cope with dumb devices and dumb applications. If you have intelligence at the edge, you can actually manage a much simpler network based on datagram switching, where data can be lost, reordered, even replicated, and it's up to the ends to actually recreate the original stream. And as long as you've got an adequate enough network, you can even recreate the implicit timing. In other words, voice and video works simply because you've got smart enough edges and enough capacity in the network. You don't have to jam the network full of expensive equipment, heaps of software, masses of complexity, and pay an enormous price to be able to talk through an IP system.
At one level, you've shifted where the cost is, because the fact remains you have to do work. Work has to be done, but you're saying we have the computers anyway. We want the handsets to be smart. They have to have the processing capacity. We want the ability to do the work, and it's already implicitly available in edge devices. How about we use that to achieve an outcome? And the second thing you said is enough bandwidth. So it isn't as simple as we can fit this down a thin piece of string. You do have to say, why are we constraining the world to be thin bits of string? How about we treat the world as having a lot more bandwidth than we used to think was the limit? Which, by the way, is pretty straightforward to do now, isn't it?
Well, that was the second part of the story. So the first part is you don't need to stuff the network full of extremely expensive technology to cope with dumb applications. My phone wasn't doing anything, my smart device, until I started talking. It's not as if it's lacking processing capability. The marginal cost of having it do some work in terms of adaptation of transport is zero. Whereas in the network, there's lots of things going on. It's actually expensive to do this. And so the first thing is you're spending the wrong money in the wrong place. But there's a different thing that's also happened. And I blame Moore's Law, many things in Moore's Law.
You've brought Moore's Law to the table.
Well, we live in a digital world.
I do actually think it's applicable. I think there's a quality behind things naturally improving in their computational capacity or size at that pace that has fundamentally altered how we think about the problem space. So I don't think you're wrong to do it.
At great expense to the Australian nation, it had built a new fibre-based undersea cable connecting Australia to basically the US West Coast, Pac Rim East and Pac Rim West. And it was a massive cable. It supported 500 megabits per second of capacity on each cable, and it cost $1 billion, and it was very expensive. And the network had to ration people's use. And this wasn't just one cable system. It was the entire underlying communication system, which was based on It's a scarce and expensive resource. We, the network operators, are the gatekeepers of that resource. We will perform rationing and we will operate this system at a price premium to make sure we're not overwhelmed.
Pricing was deliberately used as a mechanistic approach way above the individual network conversation level to put constraint on behavior. We're not talking about price comes into the packet. They didn't have dollar signs literally baked in. We're talking about the consequence of your behavior when a bill arrives being back pressure for the next cycle of using the resource.
Right. It's what we call in economics a scarcity premium. And the operators of that system, the rationers, were quite happy to basically say this costs a whole lot more to you than it did to us to make it because we haven't got enough and we have to ration it out. And quite frankly, cost, price, is the way we're doing that distribution function. Now, over the years, Moore's law has turned our 500 megabit per second subsea cable into what? 20 terabits? That's 20,000 million bits per second.
Yes, 20 million times faster than
yes.
we had.
Yes, and it costs the same. In fact, it costs half the amount, about 500 million to do this rather than $1 billion, even in just straight dollar terms.
Strangely enough, the marine fuel oil that powers the ship to deliver that cable and dig the trench has not increased in cost 20 million times. So the actual cost in terms of doing the ship side hasn't changed.
Right. The comms world has magically shifted from scarcity to massive abundance. And this whole idea that I need to arm my network with hugely expensive cutting-edge technology, SRv6, RSVP, TA, blah, 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 is basically, I think, a con by the co-conspirators of the carriage industry, the vendors, to try and extract some money from an otherwise almost bankrupt industry that has little residual value. Comms is now so abundant, you could think of it as sewerage. It's a mere undistinguished commodity. Everything happens at the upper level. And that's just the simple sort of transformation that I would come home to Moore's law with better digital signal processing. And they improve every year. We can jam more data down the same piece of glass.
Yeah.
And it's as simple as that. And we keep on getting better.
I do like this part of the story, and I think it's an important part of the story. But there's a part of me that's also saying, now hang on a minute, Geoff. Let's go back and talk about some other things that you've brought to the table. The nature of communications for you and me to be talking now has subtly shifted. You are getting packets that are caused because I ultimately sent packets into the network. Are you getting the same packets I put in? No, not necessarily. This is probably a mediated conversation. The intermediaries, the centrality thing that we've talked about, means that an awful lot of these packet flows are now heading to very short distances from where you and I are to do their primary task. And that's introduced the subtle shift here. The cost component of making all this stuff work isn't the congestion in the fiber. The cost congestion here might be switching bandwidth in a DC, or it might be the ground cost of building out that DC. There are still costs in this network.
The voice and video that you and I are having right now, and indeed when it gets, done in real time, is kind of different to the voice and possibly the video that happens in a replay. And I think we can distinguish between the two. This recording will go out onto the interwebs. Here's a podcast from Geoff and George having a talk. And it will get loaded into not one data center, but many. Why? Abundance. It's cheaper to do it that way than to broadcast it or at least house it in one spot and get the world to suck from just there.
Right.
So we send it out everywhere. And quite frankly, listening in non-real time, it's a different kind of problem. But you and I talking and exchanging video is not a mediated thing. And in fact, on my browser is the WebRTC, the Real-Time Communications Toolkit, and on your browser is yours.
Yes.
And they are sending packets to each other. We relied on a mediator to set it up, but after that, the packets are the packets. They just go end to end.
Right.
The issue is we can tolerate a certain amount of network distortion of that packet. and still have, this is Geoff, he looks the same, and his voice sounds the same, without going, oh, blub, 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 and dropping down into garble. And that next trick of making sure the network doesn't distort the implicit signaling in those packets and their timing is the next job, congestion avoidance.
We've got people who are in a marketing space who are looking to deploy complex solutions, RSVP, the TE models, SRv6, things like that, in order to make this problem go away in a fashion that suits them for their needs of sold goods and services. And you're heading towards saying, if we could find ways to do simpler methods of flicking, you need to modify your behavior. And if we could exploit all of the intelligence built into your system and my system, we might be able to get to a happy medium for a lot less work. That seems to be where you're going.
Right. The load that my device at this end puts on the network is elastic. It can repair damage to some extent. It can adjust to the conditions of the network. It's not intolerant. So I don't need a network that carves me out an assured path. It's a bit like the road system. When I traveled to the shops, I did not have a lane reserved for Geoff, clear channel, let's go to the shops, no one else intrude in my lane. It doesn't work like that. And we can all laugh at that going, well, that's ridiculous. But in the networking world, that's the goo that they're trying to sell. It's the same goo.
You and I have traveled to economies in Southeast Asia that we don't have to name, where we have stood by the side of the road and watched the local police doing exactly that, creating clear channel for very important people to drive down that road.
The problem with analogies is they often fall apart.
Yes, but specifically, Geoff, although you are paid a lot of money, you're not paid enough to get that service. So for the context we're talking in, that doesn't happen.
Right.
Baked into the IP stack that you and I are living in was ICMP. And baked into ICMP was the idea you could use an ICMP message to say, whoa, buddy, back down. Could you send less? So haven't we always had this?
Well, that was always a thought, always in the design of packet-based networks. Because once you drop the idea that the network is the arbiter, the rationer, the police of using the network, then how do you signal to a sender, whoa, buddy, that's unfair? And so you've got to actually drop further back into going, I have this network full of senders and receivers, and some senders are receivers at the same time, full of a bunch of people producing packets and consuming packets. What am I trying to achieve? Does everyone get 64 kilobits per second of clear channel? Of course not. You get what you need. But there's a couple of overriding tenets. Firstly, everyone should be efficient. What does efficiency mean?
Oh.
Don't leave the network idle if you have things to send.
Aggregate across all the people in the system. You're seeking to have as few moments where the network isn't being used as possible. I mean, obviously, if we are humans and we're asleep and there are no machines doing their job.
If there's nothing to say, idleness is fine.
But if there's more things to say than capacity in the net, leaving space and time on the net not used is inefficient.
Inefficient. So if there's space in the network and there are folk wanting to send, you failed in the job. So efficiency is, leave no idle spaces. If there is demand, fill it.
Yeah.
That's the first job. The second job is actually somewhat odder, and it's everyone should be fair to everyone else. Wow. So I don't need a network to police behaviour. No, you don't. But what you do need is if you imagine that every packet has elbows.
Sharp elbows.
The amount of pressure it puts on all the other packets should be the same as all the others.
Right.
So in other words, in a system where all these packets are jostling, oddly enough, that system where every packet exerts equal pressure creates a rough sharing.
Yeah.
If you had 100 packets all competing and they exert the same pressure as everyone else, they'll actually equilibrate and give themselves 1/100th of the common resource. Fairness.
if we just briefly step sideways, there have been things that have developed over time since the birth of the internet and the birth of Ethernet, where people have said, I'm going to take a different path. So, for instance, aircraft digital communications inside the aircraft. The devices that do that are basically Ethernet switches, but they're running a version of code that said, for the purposes we have, we're going to convert this to a time division multiplex network, and you port number 6, you have exactly these time slots to fill. And if you've got nothing to say, no one else is going to talk in that slot because I am guaranteeing you that slot. But they've done that in a highly constrained world where it's wings flapping and lights flashing and
keeping the machine in the air, George.
keeping the machine in the air. And they've made a rationing decision that is appropriate for their needs. We're not talking about that world. This world we're in, you and I are in, is a world of totally unrelated, almost random communications. There's no rationing scheme that's been designed to guarantee that behavior.
Right.
We're doing a different way of controlling use of this space with our elbows.
With our elbows, because if you seriously have the money and the need to guarantee availability at all times, then the real answer is roll your own fibre. Stop using a shared common medium, because we can't reserve in a shared common medium and still get efficiency. Can't.
Yeah.
So we're talking about the public network. We're talking about the great unwashed masses, you and I, but we're talking about sharing a common resource.
Yeah.
And the objectives then are efficiency and fairness, because, that's the world we've chosen to live in.
Yep. So I thought the elbows were ICMP. I thought ICMP baked in was the way I got to prod my elbows and say, don't do that. You're saying there's a better way.
Well, it was called source quench, and it didn't take long for folk to realise that source quench is not validated.
Not validated?
I'm a sender, and I'm just sending packets into the network. And you, George, take exception to my profligate behaviour. So you manufacture a synthetic ICMP source quench and send it to me. And when I receive this source quench, I have no idea that it's just George playing games with me. I think it's from a router on the path and I'm being too profligate. So I react like I've been slapped in the face with a wet fish. I stop sending. I back off. But it wasn't a real signal. It was just some people trying to shut me up or otherwise play.
So we need something that is simple and that's in the control mainly of people at the ends of this thing, but maybe along the path a little. I think I could imagine that's useful, but it's got to be valid and it's got to be a testable proposition, and it probably needs a modicum of signalling that you said it and they got it.
Well, the first reaction to this, now we've jumped into from not IP datagrams into the world of TCP, the Transmission Control Protocol.
Right.
And this is a kind of special protocol. I think it's the intellectual heart of the entire internet fabric, because it's what we call a classic sliding window protocol. I send you data, but I keep a copy. And every time you receive a packet of data, you send an acknowledgement, a simple, smaller packet, same protocol number, that says, I received up to byte 450 of your stream, Geoff. I can then look at my window and go, well, okay, everything up to byte 450 has been received by George. I can delete that data from my sliding window, and then I can open the window up to compensate for the data that's gone and send you some more data.
Yeah.
So it's a pacing protocol that says every time I get an ACK back from you that says you received data, that tells me, oddly enough, a packet has left the network. I go, aha, there's now room on the network for another packet. So you can think of this as a gigantic conveyor belt.
Yes.
Every time I get an ACK frame, I send the data frame back in, and the belt has precisely the same amount of data continuously. Data goes forward, ACKs come back, steady state.
Right. And if we look at this, both you and I have some degree of influence over the rate of play. If I choose not to tell you I've got things, you're not going to send when your buffer fills up.
And I'm going to stop.
And if I have told you you're free to send things, you're also free not to send them.
Right.
But you can, in principle, control the rate because you can choose not to send. We both have a role.
Once you tell me you've got it, that's it. I've forgotten anything I did. It's over. But yes, how fast should I put things onto the network is not given here. We don't know.
Yeah.
So if you look then deeper into the network, you find there are two things. There's transmission, which is indeed a pure conveyor belt.
Yeah.
I put a packet in, it goes to the other end, speed of light, speed of, signal through copper, whatever, and pops out the other end. Totally deterministic. It might get corrupted, bit errors, radio, whatever, but on the whole, packet in, packet out. But the rate of sending is not necessarily equal to the capacity of the next circuit. So I need to adapt. And the way we do this is every single link has a buffer, a queue. So that when a packet gets to a switch and it says, well, dear packet, you need to go out interface 3, but it's busy right now coping with another packet. You're going to have to wait until I've cleared that packet before sending you.
Yeah.
So it pops it in a queue. It's human behavior, You want to get onto this road in your car, the road is full, wait for your turn, buddy. It's exactly the same principle. So the network is full of queues and links.
Yeah.
Now imagine what happens when I send a lot of data. A lot. It overwhelms the link, and then the queues start to fill because I'm still sending. And then the queue gets full.
Right.
Full. What do you do with the next packet?
You got to throw it away, Geoff. There's nothing else to do.
It's IP underneath all this. Every packet is an adventure. Throw away a packet is perfectly fine. Perfectly fine.
You and me sending signals, I got that. And we've got queues come in between, which means along the path between you and me, people can stack up a little pile of them and let go. And we've now arrived at, if you're one of the people stacking up a pile of packets and your stack is full, what are your options? And your options are throw something away.
You've got no other choice. So it doesn't actually require a source quench or anything. You just throw it away.
Right.
That's perfectly fine. But let's think about the poor old receiver. I received packet 3, ACK. I received packet 4, ACK. I received packet 6.
Hang on.
Oh, hang on. Where's 5? I'm going to wait almost no time, but a bit. Packets might have been reordered. But pretty soon I'm going to say, hey, Geoff, I'm not going to ACK packet 6.
Yeah.
Because I'm missing 5. So tell you what, bud, I'm going to do a duplicate acknowledgement of 4, saying I've got up to 4, but you cannot get rid of 5 because, I haven't got it.
Yeah.
Now, that duplicate ACK is an unambiguous signal of loss. And it tells me two things that are interesting. One, I need to resend packet 5. But the next one is a bit of a leap, but it's true. I'm going to assume I was sending too fast.
So it actually requires two behaviors in you. You said with the window, when you've received an ACK, the past is gone and you forget about it. You just slightly modified that. The past is gone, but remember the last thing you had ACKed, so that when you open your window and send stuff, if you see a repeat ACK against the last thing you send, you've been told loss has taken place. You have to remember a little bit more. You can't forget all of the past.
Well, the number is actually a sequence number, and it's the number of the last acknowledged byte. And so the calculation is really easy. The first packet in the queue has a byte number. If the ACK value is less than that number, it's a duplicate ACK.
Right.
So I'm not dealing with packet numbers 1, 2, 3, 4, 5. Oddly enough, TCP is a streaming protocol, and you actually number the bytes, which is its own problem. And it's all about high speed. And let's not go there because, we haven't got time today. But, this protocol is kind of magic insofar as if I interpret duplicate ACKs as I'm going too fast, then I need to stop sending to let the queues drain. Oh, good. How long should I stop sending for? Oh, I don't know. As long as the queue is big. Ooh, now there's a clue. What if the queue held the same number of packets as the link that it drives? So if the link could contain 3 packets, let's make the queue contain just 3 packets.
Right, but that's magic knowledge, Geoff.
No, this is the design of networking. This is the bit that fills in the gap of what do you do when you get a duplicate ACK. If we build the networks such that every link buffer is equal to, in number of packets, the size of the link that it's driving.
So every point-to-point link, every party at either end of a point-to-point link makes its buffer equal to the number of packets that can legally exist in flight between those points.
Right.
Then by definition, if something goes wrong and you have to calculate the question, how big is the queue, you know.
I know. It's the same as the amount of data I can send in one round trip time interval, the time it takes to send a packet from you and an ACK back. Wow.
So am I right in thinking that this actually really is the law of physics coming up, Geoff, that if we've got a length of fibre...
No, it's not.
If we've got a length of fibre between you and me that's a foot long, we can store less data in it than if that is 1,000 kilometres long.
Yes, of course. It's physics. Why I said no, the law of physics, is we'll get back to buffer dimensioning in a second. But the whole issue is I now know how long to wait. I wait for that so-called round trip time because every time I do send you a packet and I get back an ACK, I've got my own clock. We've all got clocks. Tick, 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 tick. You're 22 milliseconds away. So when I get a lost signal, I know how long I should back off for to let the queues drain.
Yeah.
Because if I don't send any more, then basically what's in the queues will flow outwards to you. And if I resume at the end of one round trip time, guess what? You will receive a constant flow without interruption. You will see no idle time.
So you know two things. You know the byte number, last act, and you know the round trip time between those points, and you pace your behavior so that if you ever get a loss in that, pause for the round trip time and then carry on.
At a lower speed.
Three things.
Because you just filled the queue. So obviously you were sending too much, buddy. So I do two things. I wait to let the queues drain. And now the next trick, I'm going to send at half the rate. Why half? Because the queue size is where the other half of the packets lived. And so it magically forms up that if you just think of this as one connection through a multi-hop series of links with queues, then this just works. I keep on going to effectively twice the capacity of the path. I fill up the queues. I get a drop. I wait for round trip time. Queues go away. I start sending at half the rate. The next packet will fly straight at you because the queues have been drained. Oddly enough, efficiency, 100%.
Well, it sounds like there are periods when you're not using the link and you have to assume someone else fills that hole.
Oh, no. I haven't talked about, hell is other people, I think, as Jean-Paul Sartre said. I haven't talked about other people yet. It's just you and I and an otherwise idle network. And this is the theory of congestion flow control.
Right.
Now, we introduce the hell of other people. And this makes life fascinating because I'm not the only person contributing to that queue. What should I do? There was a theory, and it wasn't a very strong one, but it was a theory that with multiple senders, each with different round trip times, each with, all going through the same link, if you all used the same algorithm, two things would happen. Firstly, the queuing behavior would be most influenced by the biggest of the senders. Secondly, if everyone used the same flow algorithms, you would each get 1/nth of the share of that link.
But those two statements are in conflict because if it's most influenced by the biggest, how can there even be a biggest when you've come down to having 1/nth? Doesn't that imply that some amount of the link isn't being used?
It wasn't the best of theories.
Right.
And after about 30 years of staring at networks and queues, we're kind of coming around to a new theory.
Right.
And it's a fascinating theory because it's actually helpful. Don't forget, the faster networks get, the more expensive it is for the memory in that queue. If I'm driving a terabit per second link, I need to pull a terabit per second out of that memory bank. What manufacturer makes memory that can deliver sustained a terabit of data from memory?
That's not cheap memory.
Trick question. No, it's not even expensive memory. It does not exist.
So we're no longer bound by the speed of the link. We're bound by the speed of getting things into and out of the buffer.
Maybe it's the wrong theory. You see, that buffer memory is the most expensive memory in the router. It's the most expensive memory you can buy. We use every parallelism trick in the book to try and make it scale up in speed, but it's really, really difficult because speed has not changed. Moore's law is not about double the speed. It's double the chip density. The clock size has been static for years. But all of a sudden, these folks staring at queues came up with a fascinating answer. And it says, it doesn't work like that, dude. The buffer size is not just the bandwidth times the delay. The buffer size is the bandwidth by the delay divided by the square root of the number of sessions.
I hate it when people bring square roots to the table.
I know. Let's say a 1 terabit per second circuit, and it has a 100 millisecond of delay. Simple stuff. 12.5 gigabytes of buffer, right?
Yeah.
But let's say that same terabit of circuit carries 100,000 flows. I don't need 12.5 gigs of memory. Do you know how much I need? 40 megs.
Because you divide the initial
by the square root of 100,000.
If you have more people involved, the amount of buffer goes down.
Savagely goes down. It's kind of what saved our bacon.
So I'm kind of intuiting that what happens as a consequence is the buffer fills up and more people get a signal. You just had a loss event and more people have to go through some kind of backing down, and therefore more people balance their traffic out to be at that mythical 1/nth. And at that point, everybody's pacing to match the buffer.
This is a result that is experimental, not analytical. It's what we've observed.
It's been seen.
It's been seen, and seen a lot. And it's kind of, in some ways, intuitively obvious, particularly with that buffer bloat topic that circulated for years, that networks were continuing to over-dimension buffers. Why? Because I can sell customers really expensive routers with a huge amount of high-speed memory that is actually making life worse, not better.
Well, it looks great in the showroom when there's only you and the other end. It's when you deploy it in real life with hundreds of thousands of users, you start to find out it didn't behave the way you thought.
So let's take that 40 megabytes. How much memory can I put in an ASIC that also does switching? So I've now got a chip that's divided into 2 bits. Let's say 40% of the chip real estate I'll use for my switching fabric, the cross switching, right?
Yeah.
And then I've got 60% of the real estate that I can use for memory.
Yeah.
Now, in general, I can do around about 40 to 60 megs of memory on a single chip.
This special incredibly high speed memory.
Yeah.
Because ordinary memory, the densities have reached the point that you could fit gigabytes, terabytes on the chip.
No, I don't want to. I want really, really high speed. So I've now got a terabit per second switch with 40 megs of buffer. And as long as I'm in the middle of a really busy setup with a huge number of flows, it will just work.
You need the high number of flows?
So let's say if you're Amazon and you're designing your switch fabric, Lincoln Dale's presentation at AusNOG this year, and let's say that you didn't want to buy vendor equipment because it contains 60 million lines of code that you're never going to use. Let's say you want to trim it down, automate the hell out of it, and just switch.
Right.
Well, you're inevitably led to, I'm going to do this on one chip. I'm going to use about 64 megs of memory in the chip buffer, and all I'm going to do is switch. Wow, this works.
Get rid of all that smart, all that extra technology, all those complex additional features. Just do packets in, packets out, drop when buffer full.
Not the only ones who have reached this conclusion, but, you can see now how we scale, how we actually make these enormous systems work. And it's kind of the initial theory, this concertina-like behavior of TCP, faster, slower. And then if you put them all together, the amount of buffer demand starts to drop, which actually means you can squeeze a huge number of sessions in on the one switching fabric. And oddly enough, the more sessions you can squeeze, the lower the aggregate memory demand. Wow. This is one case where practice actually runs in your favor. It's a stunning answer, isn't it?
So that's very unexpected, Geoff, because I thought we'd be heading to a middle ground where you're saying these complex protocols like RSVP don't do the trick, but if we do just enough additional signaling, we can get the benefit. But you've actually said just stick with straight TCP and change your expectations of behaviour and remove all the complexity from the switching components. It turns out things work better than you thought.
I'm going to rephrase an old adage. I think it was from Android's Linko, but I think I was guilty of saying the same thing as well. There is no problem that more bandwidth doesn't fix. You just add more bandwidth. It's cheaper and simpler. That if your real problem was, I don't have enough network to carry the traffic, stop trying to ration, stop trying to condition, stop trying to colour the packets red, green and purple. You're wasting your time. Bring up another colour. Add bandwidth. Because if you do that, everything else works in your favor, because then you can get back to a very simple task. And what about TCP? Well, fascinating. Do I actually need to rely on loss, or can I try and sense the onset of queuing is where we are at the moment in research?
Right.
And it's kind of, well, loss is a bit catastrophic. It's like driving your car faster and faster and faster until you have a catastrophic smash. Oops. What about if I keep on driving faster until I nudge the car in front of me? No damage yet. No damage. Just nudge and then back off.
Dear listener, please do not drive like this in any economy anywhere on the planet.
When Geoff is on the road, stay clear. Same thing. But, you think about what's going on there. If I can just do this to when queuing starts, not when it collapses, then oddly enough, the winner is not the queue. The winner is the TCP session, because I waste no time in repairing packet loss.
Right. If you can target to knowing when you're using the appropriate amount of available buffer,
yes,
target it, then you don't incur the cost of a loss to be there. But that does beg the question, couldn't we have the simplest, the most lightweight of signal to flick down the line? You're getting close.
And this was an idea from the 1980s, early 1980s, from Digital Equipment. And it was called the Explicit Congestion Notification.
ECN.
ECN, an otherwise unused bit in the IP header. And when you get a packet and try and put it on the queue, if the queue is looking pretty filled, just mark the packet. Well, so what? At the receiver of that marked packet, because you're running TCP, in other words, there's a backward flow of the ACKs, take that signal, there was congestion on the inward path, and send that back as I saw a congestion signal in the TCP ACK.
Wait, you just did, if I can use a horrid legalism, didn't you just do a layer violation? That you put a signal in an IP header and you acknowledged it in a TCP transaction.
Yeah.
That's weird.
Yeah, I did. Well, it was kind of, if you want to know when queuing is starting, why not ask the router who is starting a queue? In fact, why not get the router to tell you?
I kind of like this, Geoff, thinking about this, because you said earlier ICMP couldn't cut it because anyone along the path could stuff in a line.
Yeah.
But you've just inserted into this where you get the IP signal, you're going too fast, you get it before you've incurred a loss consequence, and you signal back in TCP, somebody said something.
Yeah.
There's a bit of acknowledgement that this event took place. Is this harder to forge?
Well, it's harder to forge. And it's been around for years. It was an experimental RFC, then a standards track RFC, and a few folk have given a lot of interest in it. Apple and Comcast have started a thing they call low latency, it's L4S, low everything, but high scalability.
Right.
Problem is, it's a specialized solution for a specialized environment. The world doesn't do this. In APNIC, we started measuring ECN, and 2 to 3% of users sit beside equipment that does ECN. It's not there.
So if I go to another story we've covered on Ping, Other protocols have observed the behavior that when you include fields in headers of packets to say we think this might be useful later, there's a thing that's being called greasing.
Oh,
You need to periodically change the value you send, because otherwise intermediate systems go, that field is 0. If it's not 0, I'm throwing the packet away.
I'm making the field 0, and ECN suffers from that. Your marked IP packet gets reset.
Because we didn't do greasing down in the IP layer when we said how to do IP, these bit fields can't reliably be sent in the public net. But if we're talking me and my fabric, I can run systems that do this. And if we're talking me to a CDN, they could run systems that do this.
If you're in a closed shop, go for it. If you're out on the big public internet, it doesn't work. So how else do you do it? Well, I get back to BBR, the bandwidth bottleneck protocol, which is fascinating. How do I know when queues are forming? I don't get out a little hammer. I get out a big mallet. And for one round trip time, I hit the network with my mallet. What do you mean? I send 25% more packets for one RTT interval.
A lot more than you think you really should.
25% more than I was sending.
Yeah.
And it's kind of, did you feel that network? How do I know if you felt it? I look at the delay. Because if those 25% extra packets ended up in the queue, then for that round trip time, the measured round trip time will get a lot longer. And if that happens, I know I was already at the sweet spot. I was already at the point where queues were starting to form, because the one interval when I dramatically went overboard, I saw an extension of time to get the packets through because queuing was happening. And don't forget, in the next round trip time, send 25% less to drain the damage you just did.
You know that you were closer to the sweet spot. It might have been a little ahead of you, but you don't think it's radically ahead of you.
Whereas if there was no change in the round trip time, I can go 25% faster immediately. It's a very aggressive protocol.
It sounds like it has a risk of being greedy against other people's behavior.
Again, we get back to the two things I was talking about at the start of this: efficiency and fairness.
Fairness.
BBR does this trick once every 8 round trip times. So if there's idle capacity, it won't be idle for much longer. At some point, the mallet will come out within 8 round trip times, and, BBR will hit the network and go, can you take more traffic? So it is extremely efficient in finding the ceiling. Is it fair? Ooh. When you've got other BBR sessions, it's kind of fair, but it's not very fair. One session might end up winning, the other one losing, and you can't tell. Is it fair to all the other things that are still out there doing loss-based congestion?
No.
Oh, yes, exactly. It kind of overwhelms them because it's more aggressive.
Right.
Your elbows are longer, a lot sharper, and they reach further. You tend to put undue pressure on everyone else. And the designers of BBR have gone through BBR version 2, which was kind of too wimpy. It sort of cut off the aggressive parts, and in the end, it deferred all the bandwidth to all the loss-based systems. Didn't end up with much favour.
So again, this is experimentally driven.
Oh, yeah.
Can we tune this right? BBR's hunting for a magic point, and that point is be a little more aggressive to test if there's room, but do a better job of fairness when you decide you need to coexist. That's really quite an interesting outcome, Geoff. That's going to an interesting place.
Well, that's BBR v3, which is still being worked on, but, tweaking is happening. From a purely selfish perspective, I really like BBR v1, but, that's a bit like driving a bulldozer. Everyone else clear out because you've got no choice. So it's kind of fascinating, George, that the answer is not to put more stuff in the network, to make the network operate fairly and efficiently. It's actually to be cleverer in the endpoints and treat the network as a very simple, very dumb set of switches and queues. And to my mind, that's been the entire magic of the internet protocol for the last 30-odd years. And what do you say to SRv6 and RSVP and TE and so on? You might have a use case in your private world, and that's fine.
Yeah.
But if you try and think this is good for everyone,
no,
I think that's delusional.
Yeah.
It's just not true.
The ECN story in this is perhaps a little unfortunate. If we'd had the concept of greasing and if we had a clear channel signal for something mechanistically simple like ECN, I personally think that might have been nice. But, wanting a rainbow pony doesn't get you one, right? This is the world we live in.
Do you do the ECN marking when the queue is full, when the queue is empty, when the queue is half full? And I'll tell you what, if there's choice, everyone will have a different choice point. What does ECN marking actually mean?
Yeah.
Should I react quickly? Do I have time? And so all those uncertainties, I think, sort of came that ECN was an interesting approach 20-odd years ago. And it's interesting in a closed world, if you can define the space absolutely.
Yeah.
But out there in the big, great unwashed internet, no, push it out to the edges. Make the end TCP protocol engines do all the work. And they're quite capable of doing a really good job.
Yeah. I think it sounds like people should maybe tune into the recording of Lincoln's talk at AusNOG and get a handle on how Amazon's doing this.
Assuming they recorded it. No promises here. But you might want to listen to some of the talks about high-speed data center switching. And there's a few going around right now about, what does speed mean and how do we achieve it? And part of it is we've got so specialized these days in those data centers. You can't just use commodity, rack equipment. You really are saying, if I want terabits running through this equipment, I need to actually go very close to customized solutions.
But those customized solutions, it turns out, are significantly simpler in some senses.
Oh, yes, it's like a racing car. You take out all the bits of comfort. Nothing's left that I switch and I have memory. What else do you do? I don't know. There's nothing else to do.
Yeah. Geoff, that's been fascinating. Thank you.
It's a pleasure, George, and I hope listeners found that interesting. You can find a write-up of my work with trying to measure ECN on the APNIC blog. I think it'll be out very soon, or certainly by the time this is aired, about our efforts to try and capture ECN in the wild and what it might mean.
We'll make sure that references are put into the blog that goes with the podcast. Thank you, Geoff.
Thank you, George.
If you've got a story or research to share here on Ping, why not get in contact by email to ping@apnic.net or via the APNIC social media channels. Also remember the measurement at apnic.net mailing list on Orbit is there to discuss and share relevant collaborative opportunities, grants and funding opportunities, jobs and graduate placings, or to seek feedback from the community on your own measurement projects. Be sure to check out the APNIC website for all your resource and community needs. Until next time.